So today Josh will talk about, sorry, I forgot the title.
Something about exoplanets.
Yes, planets around other stars. Let's welcome.
Appreciate it. I want to start by thanking you. Thanks to Jim and Matthias for their offer of hospitality this year. Really looking forward to being here and learning more about what you all do. This is what the lower half of my face looks like. I think that's okay for me to reveal. And like Siao said, I work on exoplanets, and I thought I would begin just a few minutes of who I am and what I do, since we're going to be working together and having coffee together for a year. So I'm mostly interested in problems related to geometry of exoplanet systems, orbital eccentricity, inclinations, relative spacings of the orbits. And I'm mostly an observer, but the topics I work on are involved with theories for gravitational dynamics and tidal interactions, as you'll see later today. I'm also interested in descriptions of planetary systems, the distribution of planetary sizes, periods, conditional probabilities for having one planet if you see a planet of a different type, that sort of thing. And I have a kind of taste for the weird. I like ultra short period planets or young planets, anything else that is unexpected or kind of pushes the envelope. And finally, I'm involved in two large projects that I'd be happy to talk about someday, the Transiting Exoplanet Survey Satellite, or TESS, and an upcoming Doppler survey called the Terra Hunting Experiment. But for today, I thought I would focus on the topic in exoplanets I have been working on the longest. Let me just see if I can move this window somewhere else. Not destroying.
Click that. Okay.
Topic is. Let's do that, right? Oh, no, I think I'm good. Stellar spin orbit misalignment. Misalignment between the rotation axis of a star and the orbital axis of one or more planets. So to start, it's very well known, I think, that the orbital eccentricities of exoplanets have a much broader range than we see in the solar system. So these are the eccentricities of the Doppler detected exoplanets, along with the red stars. Those are the endoplanets, the planets in the solar system, which all have lower eccentricities at any given orbital distance. And we also see that there is a tendency towards circularity for the very shortest orbital distances, and that is attributed to tidal dissipation, which tends to circularize orbits. Somewhat less well known is that we have the same kind of information for the inclinations of planetary orbits above the equatorial plane of the planet. That's the obliquity of the star, the angle between the spin and the orbital axis of one of the planets. So what's shown here in a more complicated diagram are those measurements, a measure of the obliquity as a function of the orbital separation of the planet in units of the stellar radius. And if you'll just concentrate on this top panel for the coolest stars, we see that the obliquities are generally low up until about 10 times the stellar radius, at which point there's a broader distribution. And if we look at more massive, hotter stars, we see that the distribution is broad regardless of orbital distance. The obliquities are all over the place, ranging from 0 to 180 degrees. And also interesting is that if we zoom in on this region here and ask about the most precisely measured obliquities, the rare cases where we can have a measurement precision of about 1 degree, we see that they are closer to 0 than the solar system. So sun's obliquity is about 6 degrees relative to the invariable plane, the total angular momentum of the solar system planets. And there are at least a subset of systems that have lower obliquities than that. All of these facts remind me of tidal dissipation. And I'll give some more detail later. But first, I would like to explain how we obtain this information. Eccentricity, I think everybody knows, comes from monitoring the radial velocity. The obliquity, in most cases, comes from a trickier technique that involves fusing the transit and Doppler techniques. So the idea is that during a transit, the brightness of the star temporarily goes down. But if we view the same event with our Doppler glasses, sensitive to part per billion shifts in wavelength, then it looks like this. The star is rotating, and the part of the star that is rotating away from us is blue shifted, and the part coming towards us is red shifted. And usually those two sides, when we integrate the light in our spectrograph, lead to no net Doppler shift. But that's not true during transit. When the planet is on top of the blue side of the star, then when we integrate the light in our spectrographs, we get a net redshift, which then goes away when the planet crosses the symmetry axis and turns into a net blue shift on the other side before disappearing. So it's this blip. We monitor the Doppler shift during a transit. We see this little blip, and we can interpret that to get the obliquity of the star. Because if we now turn the star over to some large angle, now the planet is spending all of the time on the red side of the star. And so we only see an anomalous blue shift. So it is the symmetry and amplitude of that signal there that tells us the angle. Now, this was first theorized by Holt in 1893, and it was the first claimed detection was in 1912 by Frank Schlesinger. And that's why we call it the Rossiter-McLaughlin effect. After these two astronomers who they must have posted their papers on the same day to archive in 1924. And of course, they were studying eclipsing binaries rather than planetary transits.
I'm sorry, I blanked out while I was listening
Sure,
to this.
something about the Rossiter effect.
Right, so in the solar system, you said that the plane, the obliquity is defined relative to the total angular momentum, but in these systems,
That's right.
we don't know. We might only have the one planet, right? So there's also a little bit of noise introduced by the relative inclinations of the planets.
For sure. Yeah, there are very few systems. In fact, I can think of only one system where we measure the Rossiter-McLaughlin effect for more than one planet in the same system.
Mhm.
But that would be interesting. That would be a way of measuring the mutual inclinations between orbits, which is actually very hard to determine in general. But you're right that when we say the obliquity of the star, we mean relative to the most easily detected planet most of the time. Yeah.
So how do sunspots affect these measurements? So because I can imagine that it's temperature dependent and can that be an issue for lower?
Yeah, so sunspots do the same thing. Sunspots are little dark spots that move from one limb to the other. And so they too produce a net blue shift and red shift depending on the phase of the rotation. But fortunately, the rotation periods are much longer than the durations of these transits. The rotation period for the sun is a month, whereas these transits we're talking about just a few hours. So that would just show up as a very slow drift on top of this much shorter timescale.
Are they of the same magnitude or?
They are. I mean, it depends on the size of the spot. Depends on, if the spot is blocking 1% of the light of the sun, then that would have the same amplitude as a planet like Jupiter in front of a sun-like star. But the sun doesn't have such big spots, but other stars do.
Follow the rotation, right?
That's right.
Planet.
Right. So the spots would always go red then blue, whereas the planet need not.
I think stars already have a detection of the spots and the planet, so the spot will probably can give you some additional.
Yes. So one of the techniques that I did not plan to discuss does take advantage of those spots, because if a star has a spot, then the flux will vary gradually, as we've been talking about, as well as the Doppler shift. But if the planet during a transit hits a spot, crosses in front of a spot, then there's a little glitch in the light curve. And if you have a large number of those spot crossing events, the pattern, the timing over which they occur sometimes reveals the obliquity of the star as well. If they have long lasting spots, for example, and the planet keeps running over it, the same spot, the star must have a low obliquity. But that need not be the case if there's a high obliquity, for example. Yeah, so that's a pretty cool method. But it hasn't been as productive as the Rossiter-McLaughlin effect, because it requires a very different kind of data.
So modeling the shape of this deviation, do you need to worry about the differential rotation of the star?
Not really. I mean, if you have, for the most precise cases where we do have 1 degree uncertainties, my guess is that we are limited by systematic effects due to things like differential rotation. Differential rotation would be most important if the planet has a polar orbit. So it's crossing all the latitudes during the transit. So if we have a really high precision observation of such a polar orbit, we might actually learn something about differential rotation. There have been a couple of claims to have seen this, but they're not. We wish the data were better.
And when people are presenting results, this wiggles.
Yeah.
Do they actually model the line shape by, like
Yes.
tiling the star and, actually trying to see how it goes, or they just, take a line centroid and that's what they show?
Certainly for pedagogical purposes, it's easiest just to talk about the displacement in the line center. But when the main source of broadening is Doppler broadening, rotational Doppler broadening, it is advantageous to model this distortion directly instead of treating it like a.
So this is where differential rotation might be taken into account.
That's right, along with all kinds of other things, the turbulent motions of the stars, the convective blue shift. There are all kinds of other reasons why the spectrum of the star varies with position across the disk. So all of that would, in principle, have to be taken into account. Yeah.
So, and I think the previous slide you were showing that most of the stars were, sorry, I guess maybe a couple slides before, but most of the stars that have really low ubiquities have, or actually, no, I should say that the other way. Most of the stars that have really precise ubiquities have really small ubiquities.
Yeah.
I'm not a planet person, so I'm trying to understand, are there systematics, kind of like a selection bias effect that would lead to this? Or is this really a representative sample of what the star should be? Essentially,
The main
is it
selection.
easier to measure the obliquity with high precision if it's low?
No, but it is easier to measure the obliquity precisely when it is a cool star.
Okay.
That's why all of these really precise measurements are coming from here. And this population happens to be well aligned. And so what this subset is telling us is that maybe all of these have really low obliquities. In fact, one of the projects I'm working on, hopefully in the coming year with Gumi Stephenson, a postdoc at Princeton, is to try and revisit some of these things and see if we can, like maybe these obliquities are like a 10th of a degree. That would be really interesting to know. That would be even more evidence that they've been tidally damped. Sure. Okay, so here is some of the planetary data. And so we have examples of well-aligned systems. We have plenty of polar orbits as well, and even some apparently retrograde systems where the planet's trajectory is backwards compared to the motion of the rotation of the star. Yeah.
And the long-term trend is another companion?
Long-term trend, yeah, it's the planet. That's the Doppler signal by which the planet can be detected in its mass measured. Yeah, that's right. It's always downward sloping because when the planet is in front of the star, star is accelerating towards us, and so you have so the speed is coming at us. That's why it's always sloping down. So the slope of this line is related to the mass of the planet. Now, there is one kind of annoying thing about the Rossiter-McLaughlin effect, which is that we're not really measuring the obliquity. We have to think a little bit about spherical geometry. So here is a coordinate system centered on the star, and the orbital axis, the spin axis are labeled, and this is the line of sight to the observer. And the only interesting angle physically is the angle between the orbit and the spin. That's not actually what we measure. What the Rossiter-McLaughlin effect is most sensitive to is the angle between the sky projections of the orbit and the spin. That's the angle labeled lambda here. And to get the angle we care about, we need to know the inclination of the orbit with respect to the line of sight, as well as the inclination of the star with respect to the line of sight. Now, if we have a transiting planet, we know the orbital inclination is very close to 90 degrees, and we can measure it really well. So usually the missing information is the inclination of the stellar spin axis. And a little later, I'll talk about how we recover that information. So for now, though, this is a summary of the obliquity measurements that we have. On the upper panel, we see the planet size versus the orbital period. So each dot is the measurement of a particular system. They're colored according to the technique by which we get the information, and they're filled in if they are misaligned. I think we defined misaligned as being more than a 10th of a radian with at least 3 sigma of confidence, something like that. And then on the bottom, we have the same thing, but the y-axis is the mass of the star. So let's see, 3 things you might notice here. First of all, most of the dots are gray. I think that's gray, right? And those are the ones that come from the Rossiter-McLaughlin effect. That's been our most productive technique in that sense. The second thing is that most of the measurements involve planets up here. Those are hot Jupiters, large short period planets. And that's just because the measurements are so much easier. When the planet is big, everything scales with the square of the size of the planet. And when the orbital period is short, there's just more opportunities to observe transits. So the other thing you might notice, somewhat more subtle, is in this plot, when you look, most of the filled dots, most of the misaligned systems are on the high end for stars that are somewhat more massive than the sun. And lower mass stars tend to have more open circles. Those are not the ones that we see as misaligned. So that is interesting. What is especially interesting is that the transition from well-aligned to misaligned happens about 1.2 times the mass of the sun. And theoretically, we already know, long ago that there's something special about that particular solar mass. There's a transition in the internal structure of the star. This is a so-called Kippenham diagram, where it's showing the internal structure of stars of different masses on the main sequence. And the y coordinate is the enclosed mass coordinate. So we're going from the center to the photosphere, and the convective regions are cloudy and the radiative regions are left white. So for example, the sun has an outer convective zone, but it's very, very thin in terms of mass, it's very low mass. And around 1.2 times the mass of the sun, that is where stars go from having a outer convective envelope to being mainly radiative and then developing a convective core. So and that leads to all kinds of consequences. On the observational side.
How did the trend that you just showed relate to the one that you said on the previous slide about the temperature?
Yeah, I'm coming to that. So this is in terms of stellar mass. In terms of effective temperature, it's about 6 to 200 Kelvin. So that's why we divided the stars with a breakpoint at that point at 6200. On the observational side, it's also been long and clear that there's something special about 1.2 solar masses. I think this is one of the most remarkable plots in stellar astrophysics. It's the projected rotation velocity, which we get from the absorption line broadening as a function of spectral type. And for stars that are solar mass or less, they're all very slow, but then they just go through the roof once you go through this transition from having a convective envelope to a convective core. This is the so-called rotational discontinuity. Some people call it the Kraft break, after a paper by Kraft in 1967. And the way this is understood is that the stars that do have convective envelopes and radiative cores, it's that interface is what leads to a magnetic dynamo, a large-scale ordered dipolar magnetic field of the star, which in turn can fling out angular momentum in a stellar wind and lead to magnetic braking. So these stars have a mechanism for losing angular momentum that they inherited from their original collapse. And they're also thought to have rapid tidal dissipation. There are various mechanisms for dissipating tidal oscillations that require the presence of this outer convective zone. I'll talk about one of them later on. Whereas stars on the other side, the ones with radiative envelopes, they do not have these strong organized magnetic fields. They have no magnetic braking, and they are thought to have slower tidal dissipation. So the way that this relates to the obliquity measurements is that if you have one of these cooler low mass stars with a convective zone and a hot Jupiter, tidal dissipation is strong and the star is rotating slowly to begin with, and so it's easy to mess around with the star's angular momentum, and that leads to tidal realignment. Whereas if you have a wider orbiting planet, even if it's the same mass, tidal forces weaken very sharply with orbital distance, tidal dissipation especially. And so if those stars become misaligned, the tides do not realign them. And the hotter stars, even when the planet is close in, because the internal rate of tidal dissipation is low in those stars also fail to realign regardless of the orbital separation. So this is the hypothesis by which we try to understand the patterns I mentioned in the obliquities. We also see even more direct evidence, I think, for tidal interactions between a planet and the stellar spin in the form of the enhanced spin rate of stars with hot Jupiters. This is something that was noticed a long time ago. One of the graduate students I've been working with, Rob Takada Aravallo and Cassandra Anderson, a postdoc at Princeton. We revisited this and found that the evidence has even strengthened. So it's a comparison of the measured rotation periods of stars as a function of their age determined from stellar evolutionary models. And it's divided into, so all of these stars have overlapping spectroscopic properties. They look very much the same, except some of them have hot Jupiters and some of them have warm Jupiters, which are giant planets, but they're further out. And at any age, the ones with hot Jupiters, the blue dots, are rotating faster than the ones with warm Jupiters. And this is easy to understand in terms of tides. The rapid motion of the hot Jupiter and the short distance is what spins up the star. So we do see already that planets can affect the spin rates of the stars.
So what is this best fit line, best fit to what?
This is the Schumannish relation where the period goes like the square root of time. And I think it's just whatever Schumannish published. And if we fit that same law, but we allow the coefficient to be a free parameter, we get the dash line. So both of these are just period increasing as the square root of time. There's another pretty cool piece of evidence for tidal interactions, which is that, so if the planet really is spinning up the star, that means angular momentum is being transferred from the orbit to the star. It means the orbit must be shrinking. And there's one case where we think we actually see that happening. It's a planet called WASP-12, and it's been monitored now for 13 years, and we can see the orbital period is shrinking, something like 30 milliseconds per year. So this is the cumulative period shift as a function of time. This nice quadratic trend represents a steady decrease in the period. You know, it's like the binary pulsar. I think most people, when they see this plot, they think of the binary pulsar. And so Sam Yee, another graduate student at Princeton, has been following this system and has made arguments for why this is probably orbital decay as opposed to some other period.
What is the spin period of the star in that case? I mean, where
I don't remember
that diagram.
It is, yeah, I'm not sure if we have a measurement in the spin period of the star.
So it's not on the previous diagram?
No.
Okay.
It is one of the shortest period hot Jupiters, and that's probably relevant. It's also, so Jeremy Goodman has also been studying this because he's interested in the mechanisms of tidal dissipation. And he and some others have wondered if the reason why this is the one and only case where we see it is because the star is in a special evolutionary state, is just starting to evolve to become a subgiant, or at least it might be. And maybe that is what has activated some new mode of tidal dissipation that's more rapid than it would have been on the main sequence. This is kind of special in a couple of ways. It's not a typical system. Okay, so that raises a problem though, because if tides are realigning the stars, and they're also spinning up the stars, and the orbit is shrinking, is it possible to realign the system without destroying the planet? You know, naively, you might think that those two things happen on the same time scale. So we should never see a realigned system, you know, within a degree of 0, because the planet would have been destroyed. The orbit would have shrunk so far that it would have violated the Roche limit and been destroyed. So that raised a kind of interesting theoretical problem of how to achieve alignment without orbital decay. And Dong Lai had an interesting idea in 2012, a way to realign the star without destroying the planet. The idea is that when a star is misaligned, the tidal potential has a component oscillating at the stellar spin frequency, which is not present for an aligned star.
So can I ask that?
Sure.
So this kind of, are you having the presupposition of that these systems kind of are born not aligned?
Yeah, I haven't said why they're misaligned yet.
Yeah, what naively shouldn't I have thought? Okay, I had thought that you would think they're aligned from the very beginning, and it's a mystery why they got this.
I agree. That turns out to be, I think that turns out to be a more difficult question. So one of the reasons I've been focusing on this tidal dissipation is I think it has been possible to figure that out, that that's what's going on first, even though we still don't know why the obliquities are excited in the first place. Because as I'll show you later, there are a lot of possibilities. And there's not as much diagnostic evidence as there is for the reason why they become low. You know, there are all these clues about tidal dissipation, but the observations don't show as many clues for what caused the obliquities in the first place.
So I was having a very similar thought, but I went in a slightly different direction. And it was, where exactly do you draw the line between aligned and misaligned? And what side of that does the solar system lie on? Because we know that the solar system is fairly small obliquity, right?
Yeah. There's no sharp cutoff anywhere. We usually take 1/10 of a radian just as a round number, but what we're really interested in is the distribution of obliquities as a function of what type of planet and what type of star. And we see that there are two pretty well-defined categories with this break at 1.2 solar masses. But there's no one number that we're searching for to define, to distinguish the two.
So similar to what Matthias was saying then, so I shouldn't be thinking that like you're arguing that the solar system was more misaligned and then aligned itself somehow, right? This is a separate thing. We're really just thinking about the ones that are like really, really.
Yeah, so I consider the solar system to be pretty well aligned.
Okay.
Although, there's no body in the solar system that's capable of reorienting the sun right now. There is a literature though on why the sun's obliquity is 6 degrees and not 1 degree or 1/10 of a degree. I won't get into that now, but like that, someone writes a paper on that every few years. I mean, the most recent one said it had to do with the supernova that led to the formation of the sun. Or maybe it was a nearby supernova that happened during the protoplanetary disk phase. Others have said that it speaks of a flyby of another star that happened early on that created a warp in the orbits of the planets. So that is a separate issue. So back to this tidal thing. So Dong and I realized that when the star is misaligned, there's this component that oscillates at the stellar spin frequency. One way to think about that, and this person who taught me this is Chris Spalding, who I've been working with also postdoc at Princeton, is if the star is misaligned, then from the point of view of the star, the planet is on this misaligned orbit, and the orbit average potential of the planet is like a ring that the star is rotating within. But in the rest frame of the star, which is what we care about when we want to know how the fluid is going to slosh around, this orbit is what is precessing around a vertical axis here. And that drags around the fluid on the star and creates the possibility for tidal waves and tidal dissipation. And what is interesting about that, so he's not done yet, he also realized two other things. First of all, that frequency, the spin frequency, is slow. It's usually much slower than the orbital frequency, and it is slow enough to excite inertial waves in the convective zone. Inertial waves are these three peculiar waves where the restoring force is the Coriolis force, and they're only able to be excited when the frequency of the perturbation is less than twice the spin frequency. Of course, for this particular mode, it's always true. And he also realized that dissipation of these waves, these inertial waves, has the effect of damping obliquity, but does not shrink the orbit. And this, I don't have such a great intuitive grasp on why they don't shrink the orbit, except to say that if you have this ring and you spin a star within it, the star is not going to spin up. Like this ring is static in the inertial frame. And so there's no reason why the star would spin up due to this particular component of the tide. So that's what you want. So Dong said that because of these inertial waves, when the orbit is misaligned, you activate this different way of dissipating tidal energy, and that particular way damps the obliquity without destroying the planet. So it's a nice, tidy solution to the problem. It might even be correct. Assuming that it is correct, Chris and I have been playing around with the implications, one of which is that we might have a clue about the excitation mechanism. So for hot Jupiters with orbits, with some of the shortest orbits, less than about 0.02 AU, we argue that obliquity excitation must have happened after about 30 million years. It couldn't have been an early excitation. Why is that? Because earlier than 30 million years, even massive stars, even 1.5 solar mass stars, were on the pre-main sequence and were convective. They might be radiated today, but they used to be convective. And so if the obliquity excitation happened that early, we would see even massive stars to have been tidally realigned. Or at least we have to calculate whether that would be the case. That's what we did. And we found that in fact, is the case, that there are at least some exoplanetary systems where, assuming the story is correct, we know that the obliquity excitation happened after the pre-main sequence, after the protoplanetary disk had gone away. So what does excite these obliquities? There are lots of possibilities that have been discussed in literature. You can divide them into two main groups. One is primordial, that is, the star became misaligned with the disk, and then the planets formed within a misaligned disk. That's the category of theories I was just arguing against, at least for those especially close in hot Jupiters. And then there are lots of shenanigans that can happen after formation involving multi-body dynamics, such as Kozai-Lidov oscillations, which I'll also talk about shortly. But there are lots of variations on that theme that can, there are probably a lot of ways to mess up a system. It's like unhappy families are all unhappy in different ways. So there's another system. So most of the time, I think we don't know what's going on, but there is at least one other system where we think this story is correct, the Kozai-Lidov oscillations. And that is K2-290. This is a system I'm working on with Simon Albrecht at Aarhus University and a graduate student there, Maria Hjorth. So this was the one case I alluded to earlier, where there are two transiting planets, and we have the Rossiter effect for both of them. It's not the greatest data in the world, but for the big, easier to detect planet, we see clearly this evidence for a retrograde orbit. It goes blue, then red. And for the other planet, which is smaller and harder to measure, at least we can tell that it goes blue first, suggesting that it is coplanar with the other planet. And just the fact that they're both transiting suggests that they're both coplanar, but it's not a definitive argument. And knowing that this Rossiter effect goes blue first supports that idea that they have two coplanar planets here. And that means it's a little harder to imagine multi-body dynamics messing up the orbits. That would tend to dynamically heat the whole system. It wouldn't leave these two planets locked coplanar, at least not necessarily, whereas the star would be misaligned.
Why is it more difficult to get the other half that curve?
I think the sun came up.
New thing. Like,
Yeah, a lot of things have to go right to get these kind of data. I mean, not only do you have to have the instrument capable of doing the detection, but the transit has to be centered within the night where your telescope is located, and weather has to be clear for the whole stretch. So, well, another thing that happened, and I don't remember whether it was the case here, is that we get interrupted by transient observers who say, oh, neutron star merger might have just happened. We need to take over. And so, we need the whole night, basically. So it's very vulnerable to problems, these measurements. So the reason why we think we know the story here is that there's more we know about this system. In addition to the misaligned star and two coplanar planets, we see a third companion in adaptive optics imaging. And it's a star. It's a low mass star about 150 AU away. And it has at least properties that are compatible with a story of, I said a moment ago I was going to talk about Kozai-Lidov oscillations. That is wrong. This is a different mechanism. It just involves the torque from a stellar companion, which can tilt the disk. And then the planets form from within the disk. So this is where we think that there's been a primordial misalignment. Kozai thing will come later. So what happens in a case like that, you have a disk, you have a star, and you have a binary companion, which defines the total angular momentum, mostly in the binary orbit. The disk is precessing around the binary axis, because that's where all the angular momentum is, and the star is precessing around the disk's axis, and the star is pretty rapidly rotating at this stage. There's a strong coupling between the star and the disk. And then what can happen is that as the disk dissipates and its mass goes down, that the frequency of the disk precessions of the star precessing around the disk is changing, and they can encounter a secular resonance. Those two frequencies can match, and that causes all kinds of well, everything goes crazy, like you'll see. So J.J. Zanazzi helped us work out the story for K2-290. The idea is, as I said, the precession frequency between the star and the disk is going down as the disk goes away. The disk binary frequency stays the same. And for plausible values of all of the relevant parameters, including the known parameters of this companion, you often get a crossing of those two frequencies. And that can lead the obliquity of the star, which is usually just oscillating a little bit, to really go crazy and to become retrograde. So this is a case where we might have a secular resonance that tilted the star away from the disk, and then the two planets formed out of the disk.
So if stable companion is very close, it seems that the disk may be destroyed. And if the companion is very, very far, then the effect is probably very small. So is this like 100 AU, like a sweet spot for this?
I guess you might say that. I don't know how narrow that range is of allowed values, but what encouraged us in this system is that the measured values seem to work. But you're right, if it was a 10 AU, it would be a very different story. If it was 1,000 AU, there probably wouldn't, everything would be too slow. So maybe you're right, maybe there is just a factor of a few allowed around that range. Okay, so what is the distribution of obliquities though? Going beyond these individual case studies, we should be able to learn something by looking at the distribution. And then also, what about the smaller planets? Everything I've been talking about, minor exceptions, has been giant planets. And so a lot of the theories for obliquity excitation have centered on close-in giant planets. Maybe the way that hot Jupiters are made involves tilting the orbit, for example. Well, if that's correct, then we shouldn't observe high obliquities in systems with smaller planets. They're much harder to measure. All the signals are smaller when the planet is smaller. So how do we overcome these problems? Well, first, let's talk about the obliquity distribution. So as I said a while ago, the Rossiter effect is insufficient. It's only measuring one component of the obliquity. We need to get the inclination of the star to actually measure the true obliquity and to construct the physically interesting distribution of angles. So the way we can get that these days is that we have more stars where we can measure the rotation period, because we have all of these long duration photometric campaigns that monitor the brightnesses of so many stars. So we have lots of rotation periods these days. And that allows us to play the following trick. So if the absorption lines of the star are at least partly broadened by Doppler broadening, then all of the things being equal, if we tilt the star over to low inclination, the lines get narrower. And through that measurement, we can measure the Vsinai of the star, the rotation velocity of the star projected along the line of sight, so we have the sin I factor. If we also know V, then we divide this measured quantity V sin I by V to get the sin I. And we know V if we have the rotation period of the star. It's just 2 pi r over the rotation period. If we have the radius of the star and the rotation period and the V sin I to varying degrees of accuracy, we can derive the distribution for the inclination angle. If we also have lambda, because we've measured the Rossiter-McLaughlin effect, now we have the true obliquity. So it turns out there are 57 systems now where we can play this trick, where we have all the necessary data to construct the true obliquity. And something weird emerged that surprised me, at least, when we put this all together. So these are the measurements of lambda. This is the projected obliquity, and is a function of the star's effective temperature. And like I said, it ranges all over the place from 10 to 1. So I was kind of expecting the actual obliquity distribution would also be really broad and include a lot of retrograde systems. But that just isn't the case. When you convert them to true obliquities, you find none of them that are above about 140 degrees. And there's weaker evidence, but still evidence for a gap here as well. So there's nothing here, and there seems to be fewer systems in here too, which would suggest that there's a preference for systems near 90 degrees, or maybe a little higher than 90, like 100 or 110 degrees.
By eye, it looks very striking. Why are you saying it's not for sure?
Well, whenever you notice the pattern, and then you devise a statistical test after you see the data, you're very likely to get a low p-value.
Yeah.
So the p-value here is quite low, and I think that's what your eye is also saying. Then you have to ask, well, if the data looked weird in how many other ways would we have written a paper about it? So that's why the only thing to do is get like 10 more data points and see if the pattern still holds.
What do the colors mean?
They're just conveying lambda. So there's no extra information. This is drawn from a paper where that color is important for other charts. Actually, the other thing dangerous about visual observations is there's much less phase space here and here than there is near 90 degrees. Because of the coast, really the coast psi should be uniformly distributed if the orientations are random. So this is the plot you need to look at to decide if it's compatible with random orientations. And here it's a little less secure. You know, there still are a lot of systems that should have been here and here, but the distribution, it's not quite as compelling. So since we wrote this paper, I don't know, 6 months or so ago, I'm only aware of 2 new data points, 2 misaligned stars that can be put on this plot, and they sit here. So one of them, you know, is very compatible with this pattern. Another one sort of is, but you know, it's on the edge. So like I said, I'm not going to be completely comfortable until we get like 8 more and see if the pattern still holds. But anyways, let's play around with the idea that it's real. What could be going on here? Why would there be a preference for nearly perpendicular orbits? Well, kind of amazing is that Dan Fabricki and Scott Tremaine actually predicted there would be a peak at around 110 degrees in the obliquity distribution of hot Jupiter systems specifically. And that's because they had in mind quasi cycles and tidal dissipation as a way of shrinking the orbit of what was a very wide orbiting Jupiter down to the size of the orbit of a hot Jupiter. This is, I'm sure many, if not all of you are familiar with this term. The idea is that if you have another body in the system, star, brown dwarf, wide orbiting planet, and its orbital inclination exceeds this critical value, which is around 40 degrees, then that can cause eccentricity and inclination oscillations on the planet. And those go on for a while, but if the high eccentricity state brings the planet close enough to the star, tidal dissipation becomes important, draining energy out of the orbit and causing it to shrink and ultimately circularize. And depending on the timing of when that happens, it can leave the orbit stranded in this high inclination state. And so if this is the way of making hot Jupiters, they predicted the obliquity distribution of the stars should be very broad, but there should be a peak here, which I guess is somehow related to this this magic angle, although I don't remember the details.
Why is the spin of the star any relevant for anything?
Well, I'm not sure, but I think when Dan and Scott were looking into this, they were just taking the spin of the star to be initially aligned with this orbit and to stay well aligned. I'm not sure if they considered the coupling between the star and the inner orbit. Subsequent authors have taken that coupling into account. Maybe they did too, I just don't remember. So you really have to honor a prediction that seems to have been confirmed. The catch is that not all of the systems for which we have the obliquity measurements, not all of them are hot Jupiters. Maybe half of them or maybe a third of them are definitely not. So it's unclear. That doesn't rule this mechanism out. It just means that it's not quite the specific scenario that they investigated here.
Also, if I would make such a diagram with the observational data, I think the gap at 60,
there are too many systems in here to be compatible with the data.
And there is a kind of trough at 90, which is.
Yeah, well, you can think of it as a trough at 90 or a peak at 110. That kind of is also broad. Yeah, so I agree. This isn't like compatible in detail, but this has been such a favorite scenario for theorists. Lots of people have investigated it, before our paper about the obliquity distribution, and found that the shape of the distribution can be molded depending on the mass of the planet and probably the efficiency of tidal dissipation, all kinds of other things. You still generally get 2 peaks, but it is possible. Some of like this scenario here, it looks like a pretty good match to the data, and it was devised before the observations. Now, it's not a prediction exactly, because this is from a paper by Cassandra Anderson. She considered lots of possibilities. But to me, it means that this scenario is worth investigating further to see how widely applicable it can be made and recover the obliquity distribution that's measured.
But don't these things look a little bit wider, the zero, the part with zero? I mean, your data look like much more clumped around 0, and then
yes, you're right.
Had a broader distribution was the second peak, like what you would call the second peak.
What these theoretical distributions are missing, there should be a big peak around 0, because some of those are the tidally damped systems. Might have been misaligned that we should ignore for the purpose of comparing to these scenarios. So there does seem to be a really well-aligned population, along with a misaligned population that has centered around here.
All right, what is this efficiency parameter that's different between the panels?
Right, so I forget exactly, but I think these scenarios are for different choices of a planet mass. And this FHJ, I think was related to she did a big population synthesis model with lots of three-body systems working their way out. And I think this is related to the fraction of the systems where you actually produce a hot Jupiter.
Oh,
That it actually does manage to shrink the orbit. So it's the efficiency of this mechanism for producing hot Jupiters. I think. Okay, so that's about the obliquity distribution. Here's that plot again that summarizes all of the measurements. And what would be really nice also for figuring out what's going on is knowing what's happening down here, the small planets, where the Rossiter-McLaughlin effect is essentially out of reach. And there are some measurements here, but what this plot doesn't convey are the uncertainties. And the uncertainties for most of these small planets are very large. So we need to think, we need to come up with some different way to assess the obliquity distribution of small planets that doesn't rely on individual system by system measurements with gigantic telescopes. So the one that we have thought of is related to the Vsinai method that I showed you before, where we measure the Vsinai from the Doppler broadening. But we don't always have the rotation period. And furthermore, it's a little dangerous to select only the stars with measured rotation periods. That's a biased sample. It's going to be biased towards young stars, active stars, also biased towards edge-on stars, because the pole-on stars, the spots are just going around like that. And that means there's not much flux modulation. We didn't want to select a sample of stars with measured rotation periods, but instead we just use the fact that all other things being equal, if you have a bunch of stars with transiting planets and they are misaligned with respect to the orbits, they're going to have lower Vsinai than they would if the orbits were well aligned. If sin I were 1, you get the maximum possible Vsinai. If sin I is all over the place because the stars are misaligned, you'll get a lower average value of Vsinai. So the game is to measure the Vsinai distribution of a lot of transit hosting stars and compare it to some other Vsinai distribution to see whether it's systematically high or low. So we tried to do this. So these diagrams are the spectroscopically observed parameters and the derived stellar parameters of two samples of stars. The blue dots are stars from the Kepler transiting planet sample with small planets, smaller than 4 times the size of the Earth. And the orange dots is a control sample that we created by finding spectroscopically similar stars in the Kepler field and observing them with the same instrument, telescope, analyzing the data with the same exact software that we used on the planet sample. So everything was we're trying to be as differential as possible so that any observed differences in the Vsinai distribution will be most sensitive to. So the point of these plots is that the blue and the orange dots are kind of overlapping. They look like they're drawn from the same distribution, and that's by construction. So now here are the Vsinai distributions. Again, the blue and the orange. This is Vsinai as a function of the effective temperature of the star. You see the overall rise, because this is bracketing this rotational discontinuity that we saw on the other chart that extended much further to the left and right. And the binned Vsinai values, the averages in these bins are the diamonds. So what is interesting is that the transit hosts do seem to have systematically higher Vsinai than the control stars, at least in this range. And the control stars are presumably randomly oriented. That turns out to mean that the average value of sin I is pi over 4. It's like 0.79. And the Vsinais of the planet hosts are larger than these by about a factor of 4 over pi. So at least for these bins, it's essentially compatible with the idea that the obliquities are low. Then up here, the statistics are worse, but the evidence goes away. And these don't seem as compatible with the idea that the obliquities are low. In fact, they are compatible with the idea that the stars are randomly oriented. The planet hosts seem to have the same sin I distribution as the randomly oriented stars. And then there's one point down here where that pattern doesn't hold. So they also overlap here. So another, this
sizes of diamonds? I mean, how are they related to the dispersion?
Yeah, I think these little error bars within the diamonds are the standard
Like
deviation.
every diamond versus diamond, that's like
Yeah, just like
close to sigma detection.
each of these is like a 1 sigma or maybe 2 sigma for over here. So it's only when you combine them that you get something that's really convincing. And then there's this point down here. So
It's like
Yeah.
supernova type 1A data.
it's like a lot of things. We worked so hard to do this experiment and convince a time allocation committee to observe a bunch of random stars. It's actually quite difficult. And in retrospect, we wish we'd done it like 3 times larger. The statistics are good, but not compelling, I would say. But they do suggest that the obliquities are low for the cooler stars and high for the hotter stars, which is just what we observe for the giant planets. So it could be that the hot stars are misaligned in general, regardless of the type of planet, small or large. I'll skip the next few slides in the interest of time. Okay, there's another piece of evidence for this same pattern, which didn't come from our group. It came from a group in Tel Aviv. So their idea was to look at the amplitude of star spot variability. So spots going around, that produces these variations in the measured flux of the star. But like I was saying earlier, if you tip the star over on its side, all other things being equal, the star spot variability is going to go down because the spot's just going around in circles on the sky. And so they realized that this was another probe of misalignment. If the stars are all misaligned, let me put it this way. If you have stars with transiting planets and they're all well aligned, and they all have high inclinations, their photometric variability should be higher than a bunch of random stars, which are rotating in all different directions. Okay, so that's the given.
Explain this again. Because I didn't
Sure.
hear.
Yeah, so
Why is the-
in this configuration, so the reason the flux is varying is because the spot comes into view, goes around, goes out of view, comes into view, goes out of view. If the star is rotating like that, that doesn't happen. So there's no flux variation. There's also limb darkening. When the spot is projected against the limb, the modulation is smaller. So both of those effects together create the lower flux variability when the inclination is low. Okay, so they actually looked at the Kepler data where we measured.
This doesn't it depend on whether the spin is pointing to you as opposed to pointing on.
Correct,
If
yeah.
This side is fine with 50% of the time.
Yeah, it's sensitive to the inclination, but not to the positioning. You're right. So it's like all things. We can't measure what we really want to measure. We just measure one component. But it remains the case that in large samples of well-aligned stars, that's where you maximize the photometric variability. And all other orientations would only either keep it the same or lower it. So again, this is what the data look like. So they measured the photometric variability of all the stars in the Kepler field, some of which, red dots, have transiting planets. And again, these bigger symbols are the averages within bins of effective temperature. And here, I think the statistics are even better, that the stars with transiting planets do have systematically higher photometric variability than the random stars do. And so these are consistent with good alignment until you get to around 6,000 Kelvin when these curves cross. And at this point, to be at face value, the stars with transiting planets are oriented just as randomly as the background stars, the stars without any knowledge of orientation. And then it even goes in the other direction. That is, for the really hot stars, they have suppressed photometric variability compared even to randomly oriented stars, which is really weird because that would suggest a preference for polar orbits. The only way to do that with geometry is with polar orbits. If the transit hosts are not just randomly oriented, but actually prefer to be perpendicular to the orbital plane. I don't think we can draw that conclusion from this study because there's also a pretty bad selection effect out here. These stars are bigger. It makes it harder to detect a transiting planet. And so you only would detect them around the stars that are systematically quiet, where the photometric noise is lower. So at least part of this reversal here, I mean, everything to the right here is a little bit questionable because of that selection effect. Now they modeled the selection effect and they say that it doesn't account for the whole difference, but it's hard to model those selection effects.
So how do they control the age? Because especially for these cool stars, these spots activity is very strongly related to their age.
It's because they are externally very similar stars. They, from their colors, and now we have parallaxes. They seem to be drawn from the same distribution. So it really helps to have so many stars that are all the same color.
They're kinematically the same in the galaxy.
I don't know if this was written, I think, before it was
Oh,
actually
right,
possible.
that's right, yeah.
So I don't know. That would be
That would be
useful
a
to
good
check.
test.
Yeah.
Yeah, I think this concerns me a little bit more because I think several studies have shown that these stars with transiting planets, especially hot Jupiters, they're actually like younger.
Yeah, they've been spun up. But remember, these are almost all stars they don't have hot Jupiters. They have tinier planets in wider orbits. So there has been from the planets we know about, there hasn't been any spin up or rejuvenation of these stars. But that would be a concern to do the same study with hot Jupiters. Okay, I guess it's time for me to jump to the conclusion. So I'll just summarize what the data are telling us. So I think we can be pretty sure that massive stars with hot Jupiters are often misaligned. That seems beyond doubt at this point. Massive stars with smaller planets are also misaligned. I'm not quite sure about that yet. That comes from that statistical study, as well as there are a few individual cases where we have a massive star, a small planet, and stars definitely misaligned. So there are some increasing hints that that's the case. The low mass stars are often misaligned with warm Jupiters. Like when the separation is large, that's when we start to see even low mass stars misaligned, and perhaps modestly misaligned with smaller planets. I did not discuss the evidence for that. And the obliquity distribution ranges up to 120 degrees and appears to have a broad peak at around 100 degrees. So I will not summarize the theories, but maybe this year we can work together to figure out what's going on here. Thanks. I'm happy to take additional questions.
Gosh, it's very interesting. And the questions?
So can you just say a few more qualitative words about the physical mechanisms for tidal dissipation in these stars that are less than 6,200? So is that something related to convection or something related to the magnetic fields, or both? Is one obviously dominant over the other?
Yeah, I haven't heard of any tidal dissipation theories involving the magnetic field.
Okay. So
That's really, but it's related though that magnetic braking slows down the star a lot, and that makes it easier to change the angular momentum of the star. So in that sense, magnetism is important. The tidal dissipation mechanisms, I'm not an expert in that area. So I talked about the inertial waves, which can only propagate in the convective zone. There's also the even older idea that it is the turbulent cascade in the convective zone that is what dissipates large-scale tidal oscillations. So that requires a convective zone as well. There are internal gravity waves that propagate in radiative zones, but are launched from a convective radiative boundary. So you need an outer convective zone for those too. So I think there are a lot of theories that invoke the convective zone specifically.
A question from Scott on Zoom.
If you talked about the tidal decay in WASP-12, if that process, there seems to be evidence that process leads to consumption of hot Jupiters by their host stars on a fairly regular basis from the chemical anomalies. So if that's true, shouldn't you expect to see a subset of even the low temperature stars that are rapidly rotating?
Because they've ingested a hot Jupiter.
Right.
I haven't worked on that question myself, but I remember seeing in the literature calculations of how long that excess angular momentum would be manifest, because the star still has magnetic braking. And magnetic braking has this property that the faster the star, the more rapid the braking. And so that pulse of excess angular momentum doesn't end up lasting very long. But like I said, I didn't do that calculation myself. I don't remember the numbers.
There's a growing list of protoplanetary disks that have been observed where we know that, inclination. Is there any hope of measuring the obliquity of the T-Tauri star at the middle?
Well, yeah, without a transiting planet, it's tough. The ways you can do it are you can use the Vsinai method. if you see a face-on disk and the star has a low obliquity, you should see a really low Vsinai. But to do that, because there's so much dispersion in the rotation rates of stars, especially at early ages, you would need a lot of disks to, and we don't have that many. We have dozens, but we would need like 1,000 probably. The other way is interferometry. So if you hook up an interferometer to a spectrograph, you can say, is there a spatial displacement between the red side of the star and the blue side of the star? And that tells you the position angle of the star on the sky. But the observational requirements are very, very demanding. And that's only been done for a couple of really bright stars.
So you say here, or you show that massive stars, for example, with hot Jupiter, are often misaligned. So this means that this process, whatever it is that creates the misalignment, is is happening always.
Could be, yeah. One interpretation is that hot Jupiters, at least, are almost always, they have a very broad distribution of inclinations to start, and then around the cool stars they align, and around the hot stars they don't.
And does this put some constraint on what is the ignition mechanism that creates this?
In broad terms, it means whatever does it has to lead to a very broad distribution of inclinations.
But it's happening always. You cannot rely on a sample.
I know that's the main objection to these cosi-like or multi-body scenarios, is they seem at least a little contrived. I mean, hot Jupiters are rare. Right? You only have to do this around 0.5% of stars with giant planets. So
maybe you're saying maybe whatever brings the Jupiter in is also responsible. So if you
it's also responsible for tilting. That's right. Yeah, the shrinking of the orbit is accompanied by a tilting.
How about the alignments in ultra short period planets?
Yeah, so it turns out ultra short period planets are almost always small, meaning smaller than 2 times the size of the Earth. And that puts them out of reach of the direct methods for obliquity determination. But I worked with Fei Dai, who's now a postdoc at Caltech, to show that when you have 2 transiting planets, the mutual inclination between the ultra short period orbit and the next one out has a dispersion of around 10 degrees, which is larger than what we think the dispersions are in general. So that is at least mild evidence for a larger inclination dispersion for the ultra short period planets. We haven't related that to the stellar spin, just to the other orbits in the system. So that might be related. Anyone else in TV land with a question?
Yeah, I don't see any questions.
Okay.
So we will hold a discussion in 1 hour in February. So if you have more questions, we can discuss later with Josh together.
Thanks, folks.
Thank you.